1961, Melbourne. A woman walks in for a routine blood test, and the lab machine essentially breaks. Why? Because her blood is missing something every single human on Earth was believed to have. Every person carries some version of the Rh factor. Positive, negative, doesn't matter. But this woman? Nothing. None at all. Scientists give it a name. Null. And when they dig into why, they discover something almost impossible. There are only 9 people alive on the entire planet whose blood matches hers. 9. In the whole world. Now think about that for a second. If any one of those 9 people ends up bleeding out in an accident, ordinary donor blood wouldn't just fail to help them. It could kill them. So how do these people survive? And if this blood is this fragile, this rare, why are scientists now trying to recreate it in labs? The answer is in the second half of this video, and it might just change the future of medicine as we know it. Let's get into it. Brief pause, then casual tone for the CTA. If you're into these hidden science, DNA-driven stories, go ahead and subscribe. More of these are coming. Melbourne, 1961. A hospital laboratory, doing something that happens thousands of times a day all over the world. A routine blood test before a scheduled surgery. A woman rolls up her sleeve. The technician draws a small vial, runs it through the standard antibody panel, and waits for the usual clean match. Nothing matches. He assumes it's an error on his end. He runs the test again. Then a third time. The machine is fine. The sample is fine. But her blood simply refuses to fit into any category anyone has ever recorded. And to understand how strange that is, you need to know something science had taken for granted for decades. Every human being was believed to carry at least some form of what's called the Rh factor. You could be positive, you could be negative, but the markers were always there in some shape. This woman's blood had none of them at all. Researchers named Voss, Kirk, and Sanger take on her case, and the deeper they dig, the less sense it makes. Her blood isn't missing one marker or two. The entire Rh system, every single antigen that should be present, simply isn't there. Not weakened, not reduced, absent. They give the condition a name, Rh null. On paper, that sounds like a technical label, a line in a medical file. But when they finally look at her red blood cells under a microscope, they realize this isn't just an absence on paper, it's an absence with physical consequences. A normal red blood cell looks like a donut, round, smooth, flexible enough to squeeze through the tiniest capillaries in the body. Her cells were collapsed inward instead, folded into a fragile cup shape, as if something structural holding them open had simply been removed. These cells were more likely to rupture, more likely to be destroyed by her own body, which meant she would live with a form of chronic anemia for the rest of her life. Never severe enough to be an emergency, but never fully going away either. And she wasn't the only one, though for years, almost no one else like her could be found. Researchers named Nash and Shojania spend the next 26 years searching hospital records across the globe for anyone who shares her condition. By 1987, they've confirmed exactly 32 cases on the entire planet. Not 32,000, 32 people among billions. Here's where the story takes its first real turn. As genetic testing improves, scientists discover something almost impossible to believe. This exact condition, this complete wipeout of the Rh system, doesn't always come from the same cause. Some people develop it because of a mutation in a single gene called RAG. Others develop it because 4 separate gene copies, sitting side by side on chromosome 1, all shut down together. A completely different mechanism producing the exact same outcome. 2 unrelated genetic accidents, arriving at the identical destination. But nothing about the disease itself compares to what happens next. Because this isn't just a story about strange blood chemistry. It's a story about what happens when that blood chemistry collides with something as basic as trying to have a child. In Iran, a couple with no known health problems tries to start a family. The pregnancy begins normally, and then it ends. Not once, but repeatedly, without warning, without any obvious infection or complication that doctors can point to. Nature is supposed to be biased toward life continuing. Here, something inside her own body appears to be working directly against it. What doctors eventually piece together is this. The moment her developing baby's blood begins producing ordinary Rh markers in the womb, her immune system has no memory of anything like them. It has never encountered them before, because her own blood has never carried them in the first place. So her body manufactures a very specific antibody, one that only ever appears in people with this condition, called anti-Rh29, and that antibody begins attacking her own child's blood cells as if they were an infection that needed to be cleared. A mother's body quietly treating her own baby as a stranger, and if something this basic can turn dangerous during pregnancy, a much colder question follows right behind it. If there are fewer than 50 people alive on Earth with this blood type, what happens if one of them is in a car accident? What happens if one of them ends up on an operating table bleeding out? The blood that saves almost everyone else on the planet would be lethal to them. So who actually saves their life when it matters? The answer to that question stretches across borders in a way most people never think about. In the United Kingdom, an organization called the IBGRL maintains a private registry, quietly tracking the rarest blood types in the world. And what their records show is almost hard to believe. Out of the fewer than 50 confirmed people with this blood type, only 9 are active donors. 9 people, for the entire global population. What those 9 people actually do is extraordinary. When someone somewhere needs this blood urgently, a donor might cross a border in the middle of the night, from Geneva into France, for example. To give blood to a complete stranger, they will likely never meet and never hear from again. No payment changes hands. There's no public recognition, just the understanding that their blood might be the only match available anywhere on the planet for that particular person. Some units get frozen at -80 degrees Celsius and held in reserve for years, quietly waiting in case a scheduled surgery somewhere needs them. 9 people, carrying a responsibility that millions of strangers will benefit from and never even know exists. Which leads to the darkest question in the entire story. What happens as those 9 people get older? What happens the day one of them can no longer donate, and no replacement has been found? That exact fear is what pushed scientists on opposite sides of the planet to start looking for a way around the problem entirely. And what they eventually built sounds like it belongs in science fiction rather than a hospital. In 2018, at the University of Bristol, a scientist named Ashley Toya and his team begin working with a lab-grown line of immature blood cells called Bel-A. Using CRISPR-Cas9 gene editing, they don't stop at removing the Rh markers. They cut out the genetic instructions for 5 entire blood group systems at once: ABO, Rh, Kel, Duffy, and GPB, chasing a single goal: a red blood cell so stripped of identifying markers that almost no immune system on Earth would reject it. Bristol wasn't alone in this race. In 2021, at the Versiti Blood Research Institute in the United States, immunologist Gregory Denham leads a team using stem cells to rebuild this same blood type from the ground up. At almost the same time, in Canada, researchers at Laval University take stem cells from ordinary A-positive donors and begin reshaping them, step by step, into cells carrying this exact rare pattern. Just take a moment to sit with that. Not long ago, this blood type existed in exactly 9 living human beings on the entire planet. Now it's quietly being grown in petri dishes, in labs spread across 3 different continents, by teams who have never met each other but are chasing the same impossible goal. And this is where the whole story turns itself inside out. Think about everything this blood type has actually meant for the people who carry it. A lifetime of mild but permanent anemia, pregnancies that can end in ways doctors can barely explain, a donor pool so small it can be counted on 2 hands. By every measure, this has been one of the most fragile, most dangerous blood types a person could be born with. And yet that same blood, the version that seemed the most broken, the most incompatible with the rest of humanity, is now becoming the blueprint for solving one of medicine's biggest transfusion problems. Because the very markers this blood is missing are the same markers responsible for the vast majority of transfusion reactions in ordinary patients everywhere else. The thing that made this blood dangerous for the person carrying it is the same thing that could one day make blood safer for almost everyone else on Earth. What looked like the most broken version of human blood turned out to hold the key to fixing it for everyone. So the next time someone tells you their blood type, remember there are 9 people alive right now whose blood doesn't fit into any of the usual boxes at all. And because of them, and because of the scientists who studied what made their blood so dangerous, medicine may be quietly building toward a future where a mismatched blood type never has to cost anyone their life again.